Now that we've found an appropriate way of writing spin states, we need to define operators for spin angular momentum. In the case of orbital angular momentum, we started by postulating operators associated with the components along three coordinate axes. Specifically, we had the Lx, Ly, and Lz operators. These operators were written in terms of spatial position and spatial derivative operators. But we do not apparently have that option for the spin operators, since the spin functions are not functions of space. We were also, however, able to write commutation relations for the orbital angular momentum operators. Here we might therefore start with the commutation relations and find a representation of spin operators to satisfy those. Some authors actually regard the commutation relations as the more fundamental statement of the operator properties. If one starts with the commutation relations for angular momentum operators, one can prove that both integer and half-integer values for angular momentum are possible, and these are all that are possible.
So now we ask the spin angular momentum operators, which we write as Sx with a hat over it, Sy, and Sz, by analogy with the orbital angular momentum operators Lx, Ly, and Lz, to obey a set of commutation relations. So specifically here, we ask for the following set of commutation relations. The commutator of Sx and Sy should be IH bar Sz, and similarly, actually cyclically permuting the x, y, and z's. The Sy and Sz commutator should be IH bar Sx, and the Sz and Sx commutator should be IH bar Sy. Commonly, we're going to work with dimensionless operators, so instead of the Sx, Sy, and Sc, we will instead usually employ sigma x, sigma y, and sigma z, from which the spin angular momentum magnitude has been removed. That is, sigma x will be 2 times Sx over h bar, and so on for sigma y and sigma z. These are just more convenient, or at least more common. There's no real difference in the physics here. We could equally well work with the Sx, Sy, and Sz operators. And in this case, our commutation relations that we are hoping to have, again by analogy with the ones we found for the Lx, Ly, and Lz operators, would be sigma x, sigma y, with a commutator giving 2i sigma z, and so on for the others. So basically we're saying, let's postulate that we have sets of operators for spin angular momentum that have commutation relations that are directly analogous to the ones we found for the orbital angular momentum operators. Well, if we choose to represent the spin function in the vector format, then the operators become represented by matrices, and one set of matrix representations of these operators is this set here. So we would write sigma x as you see it here, 0, 1, 1, 0, for example, for these columns. And similarly, sigma y would take this form, and sigma z would take that form. Such matrix representations are known as Pauli spin matrices. There is more than one way we could have chosen these. In fact, there's an infinite number of ways, depending on what axis we choose for the spin. This set, which we will call the z representation, is such that the spin up and spin down vectors defined previously are eigenvectors of the sigma z matrix, and you could check that. These operators, sigma x, sigma y, and sigma z, written as these matrices, do in fact obey exactly the commutation relations that we wrote down. We can write the three Pauli spin matrices as one entity, and this is now a bold-faced sigma with a hat on it, which has components associated with each of the coordinate directions x, y, and z. So we could write this bold-faced sigma here with a hat over it. It's kind of a vector operator as a unit vector in the x direction times the sigma x operator, a unit vector in the y direction times the sigma y operator, and a unit vector in the z direction times the sigma z operator. So I, j, and k in this expression are unit vectors in the x, y, and z directions, respectively. For completeness, by analogy with the L squared operator we had for orbital angular momentum, we can also define an S squared operator. This would be the sum of these three versions of our spin operators in the x, y, and z directions, or we could define a sigma squared operator similarly. Sigma squared would be, in this notation, actually the dot product of the bold-faced sigma operator with itself, and this sigma squared operator would be the sum of sigma x squared plus sigma y squared plus sigma z squared. From the definitions for the Pauli matrices, we can see that the sum sigma x squared plus sigma y squared plus sigma z squared, which we are calling the sigma squared operator, is just 3 times the identity matrix. So you can check that algebraically. And hence we see that s squared equal to sx squared plus sy squared plus sz squared is 3/4 h bar squared times the same identity operator, which is the same thing as s into s plus 1, with s equal to 1/2, times h bar squared and the identity operator. So we can define all these analogous operators if we like to. And this means that any spin 1/2 vector is also an eigenvector of s squared, which is the same kind of behavior that we get for the L squared operator in angular momentum for orbital cases. And that spin 1/2 vector will be an eigenvector with this eigenvalue s into s plus 1 h bar squared, or 3/4 h bar squared. Now, just as any spin 1/2 vector is an eigenvector of s squared, with this eigenvalue here, for orbital angular momentum, any linear combination of spherical harmonics corresponding to a given L value is an eigenfunction of the L squared operator. And in that case, it has eigenvalue L into L plus 1 h bar squared. So, just to confirm that, the spin operators behave in a way that is still analogous to the behavior of the orbital angular momentum operators, including this additional operator, s squared or sigma squared.